All right, there we go. Okay, so we're going to talk about, it's always funny. So 3.2 part 1, logarithmic functions. So you guys might remember doing this last year in Algebra 2, and logarithmic functions can seem a little bit abstract and kind of funky, especially in the notation. So in order to help you guys understand it better, let's start with something you guys are comfortable and familiar with, right? You guys know that this is y equals 2 to the x, right? F of x, same thing as y. Exponential function. We've been doing this actually for a few days now, right? We've done word problems with them, so you guys should have a pretty good bearing with exponential functions. So just to graph this quickly, we'll make a small table. We'll pick a few x values. Those are easy x values to work with, -1, 0, 1. So if you plug -1 in for x, what do you expect y to equal? 1/2. Good, thank you. And then anything to the 0 power is always going to be 1. And then 2 to the 1, of course, is 2. So you plot your points. You draw the curve. It looks like that, right? Okay, not the greatest graph. I could do a little better than that. That's a little better. So, and also there's an asymptote at y equals 0. The whole purpose of the asymptote is to tell us what y gets close to as x approaches either positive or negative infinity. In this case, if x is going towards negative infinity, y is getting closer to 0, right? Because if you make x very, very negative, 2 becomes, basically if you have like 2 to the negative 10 power, that'd be 1 over 2 to the 10th power, right? It becomes a fraction. When you work it out, that's super small, right? That's why you see the graph get closer to the x-axis as x gets more negative. So what this tells us is that our domain won't have any restrictions, right? You can do whatever you want. The range, however, is restricted. And what's the range going to be for this graph? Good. So a lot of this should be a review, right? Now, why did I do this? Because we're going to take the inverse of this function and realize that the inverse represents a log. This is why people sometimes get confused about logs. They miss that, that key step. So this right here is kind of a key step that you have to do the inverse to be able to get the logarithm. So you have to realize that a logarithmic function is simply, let me do some color, inverse of exponential functions. That's what we are. Now we have to talk about inverses. What does it mean to do the inverse of a function? What are you doing algebraically when you find the inverse? Can you solve for y? Exactly. So that's what we're going to work on in the second half of this first page of the notes. First off, the question is asking, does 2 to the x have an inverse? The answer is yes. That's because y equals 2 to the x power passes. We did talk about this last semester, but we may have forgotten. It passes something called the horizontal line test. What is the horizontal line test? What does it entail? What does it mean? Yeah, basically, if the graph, if you draw a horizontal line and it crosses no more than 1, the inverse will be a function. So that's what it tells us, that if horizontal lines cross the graph no more than once, the inverse is a function. This should be in your notes from somewhere in chapter 2, I can't remember. Or maybe it was chapter 1, I don't know. But so there is an inverse. That's the point. Now we got to find it. Once we find it, then we have the logarithm. And that's how the logarithm comes about. It's by taking the inverse of an exponential function, isolating y, and voila, there's the inverse. So let's find it. So I'll do it over here because I'm kind of running out of space. By the way, f negative 1x is the symbol for an inverse function. Sorry for messing handwriting. Just so you know, when you see that negative 1, it's not 1 over f of x. Don't think that. It's a notation thing. It's a symbol for inverse. So how do you find it? We switch x and y, right? So what you need to do, switch x and y and isolate y. Okay. So y equals 2 to the x. When you switch x and y, what happens? You get x equals 2 to the y. Isolating y is a little tricky to do. So here's what happens. To isolate y, you write a log. How do you write this as a log? You write it like this. Excuse me. You write as y to log base 2x. So the key thing here is that this is the key concept. If x equals b to the y, it's the same exact thing as saying that. I'm using double arrows for a good reason. They're interchangeable. X equals b to the y equals log base bx are the same thing. So the purpose of a log is to isolate the exponent. So that's sometimes that gets lost in the weeds. We don't realize that that's all you're doing. We're gonna spend a whole week on this, probably in part next week too. And what's gonna happen, you'll start realizing, oh yeah, if I need to solve for an exponent, like you guys did that on the check-in, right? You guys had to solve for t, right? The time it took for the money to go from $500 to $2,000, use your graphing calculators. You can also use logarithms too. You can rewrite that equation as a logarithm, and then the calculator actually can do logs for you. You don't actually have to, if you're not comfortable with the graphing bit where you have to punch in the equations and change the window and see where they intersect, if you can rewrite the equation as a log, and then there's an actual feature in the calculator that does that for you, that might be more efficient perhaps. But the purpose of log is to help you isolate the exponent if it happens to be an unknown. You got to solve for that. You go. I don't. If you can get some, that'd be great. Thank you. So that's the purpose of a log, is to isolate the exponent. So the next thing we're going to do is we're going to graph log base 2x. So I'm going to squeeze in over here. You guys may have a little more room than I do. I'm going to squeeze in right there. And what we're going to do is really focus on the part when x and y switched. X equals 2 to the y. Because that's the same thing, right? That's the way a log is defined, right? X equals 2 to the y equals log base 2x. They're the same thing, same exact thing. So when you make your table, because x and y switched from what we did a few minutes ago, y equals 2 to the x, what happens to the x and y columns? They switch also, good. So notice how I'm going to put -1, 0, and 1, right? -1, 0, and 1, because y is now the exponent. That's probably easier to plug in for y first. Y should be the input, right? Inverse. X used to be input, y used to be output. Now it's table to turn. Now y is input, x is the output. So that means you're going to get 1/2 when y is -1 for, so x is 1/2 when y is -1, and then 1 and 2, and you plot those points. To plot those points, 1/2 comma -1 is right there. 1 comma 0 is right there. 2 comma 1 is right there. The graph looks like that. So notice how it kind of looks like an exponential graph, but it's somewhat different. Also, there's a vertical asymptote too. There's a vertical asymptote x equals 0. Kind of hard to see, but there's a vertical asymptote x equals 0. Because things switch, what do you think your domain is? What do you think your range is for this graph? Yeah, domain 0 to infinity. Yep, the range can cover all y values. The domain is restricted. So it's reversed from y equals 2 to the x. Think about it. This right here is x equals 2 to y. X cannot equal 0 if x is positive. There's no way y is log base 2x, which is the same thing as this, x equals 2 to the y. Remember, x equals 2 to the y is the inverse of y equals 2 to the x. 2 to some power, I can't make x 0. I can't raise 2 to some power and make it 0. I can't raise 2 to some power and make it negative. It's impossible. So that's why your domain is restricted. So it's reversed from the exponential graph. So very important. And to really kind of drive this point home, before we do the graph on page 2, I'm just going to kind of just jump to page 3, and then I'll have you guys go back to the end of page 1 to really drive this point home. X equals b to the y is the same thing as that. And remember, it's the inverse of y equals b to the x. The inverse of y equals b to the x is x equals b to the y. X equals b to the y can be written as log base bx equals y. This is the key idea for chapter 3. This is the glue. This is what holds all chapter 3 together. Without that, we're lost. So we're going to spend a lot of time making sure you guys get this. So we're going to spend more time on this tomorrow also. And the whole purpose of this, remember, the purpose of log to help you isolate the exponents. Because y was an exponent, wrote a log, got isolated. That's the whole purpose of it. Helps you isolate the exponent. So it gives you more power when you start solving other equations that, oh, you have another skill set. So that was what happens there. So let's go back to the bottom of page. By the way, any questions so far?
Wait.
Go ahead, Julia. No problem. Well, go ahead. Yeah, but it's just another way of writing it. Right. I mean, that's why I have the double arrows. Yes. I mean, sure, you could just leave as x equals 2 to the y and call it a day, but ultimately we're going to need to find a way to rewrite it as we get to deeper into like other equations, word problems. It's going to be more helpful, but essentially you are right. It's just a way of rewriting x equals 2 to the y. That's, if you want to leave as x equals 2 to the y, you're fine, but there are times when we do want to isolate the y value and be able to have a way to write that. So that's why we write as a log. Now, the other thing here at the bottom of page 1, our exponential function is 1 to 1. You may have forgotten what that means. The answer is yes. That's because for each x, okay, that's good. For each x, there's just one y, and vice versa. Meaning for every y, there's just one x. So also it would mean it passes the vertical and horizontal line test. So exponential functions pass the horizontal line test. We saw that earlier. It also passes the vertical line test because itself is a function. So for every x for an exponential function is one y, and vice versa. So it enables us to say that the log expression is also a function too. So logs are functions because they pass the vertical line test, but they came from exponential functions. They pass the horizontal line test. So when we did the inverse, great, we got a function. Let's do a graph. Let's do some evaluating, and then I'm done with the notes. So for graphing, this is just transformations. This is a skill set that you guys have mastered. You guys did a great job in the final exam. We've done it recently with exponential functions. We're going to do it again. And we're going to do it even more times when we get to trigonometry, so it doesn't really leave. You just got to embrace it. You probably want to start. We'll go over here. Probably want to start with log base 2x. Or it's the same thing as saying x to what power? X equals 2 to the y. Same thing. The same exact thing. Hopefully you guys see what we're doing. It's basically taking the 2 and the y. You simply switch things around. The 2 gets risen to the y power equals x. Or if you have x equals 2 to the y, you can just move things around and get y equals log base 2x. So it's basically a movement thing. Go ahead, Maddie. Yes, that's what we're going to do. Yes, exactly. Exactly. So I'm going to just make a quick table again. -1, 0, 1, half, 1, 2. Easy, right? -1, 1 half, 0, 1, 1, 2. Oops, darn it. Sorry about that. I totally messed that one up. I was accidentally graphing y equals 2 to the x, like I did about 10 minutes ago. My apologies. I was supposed to do this first. My bad. I caught myself because I knew I was graphing the wrong thing. Remember, they switch, right? I talked about that many times. I don't know why I didn't do that. X and Y switch. -1, 0, 1 for y. It means 1 half, 1 and 2. So you got to plug in for y. Y is your input. Okay, that's a lot better. And yeah, graph. Okay, so that's x equals 0. Y equals log base 2 of x. Now, we transform. What do those transformations do to the parent function? Good. Awesome. So your new table looks like this. Basically, you need to do x minus 2 and y minus 1. You got to take 2 away from x, is going 2 left. The plus 2 next to x means 2 left. The minus 1 on the outside means 1 down. So that's negative 1.5, negative 1 and 0. and -2, -1, and -2, I think. No, sorry, 0. So kind of looks like that. And the asymptote of x equals -2. Because it moved 2 left. The asymptote must change also. So you guys see how that graph looks? You take the parent function, make the shifts. The parent function, remember, is the inverse of y equals 2 to the x. What is the domain and range for this, for the red curve? Yep. Same thing, yeah. Range always stays the same. By the way, just off to the side here, remember that was y equals 2 to the x. That's y equals log base 2x. That's y equals x. You might remember these are mirror images of each other. The exponential graph and the log graph. They're mirror images of each other about y equals x because the inverse. Inverse will always follow this. Because x and y switch. Because you switch the x and y values, they just switch. So I forgot to mention that earlier. So I know I'm throwing a lot of information towards you guys. That's why we're spending some more time on this. But again, switch x and y, the inverse, the log, and of course, if you have to transform, you transform. Okay. Any questions before we do the evaluating part on the last page? Okay. Let's do the evaluation part. This is, I think, where I think logs will start hopefully making more sense when you start moving things around. You start seeing that all it really is just isolating the exponent, right? As I mentioned earlier. So like in example 3, write each equation in its equivalent logarithmic form. So log, and notice how when we write it, when we take the exponent, we will do that. Yeah, give me a sec, I'll get to that, but you are correct. But notice if we take the exponential equation, we have to identify what b is, right? What is b in part A? 12. So you're going to have to put as a subscript. Log base 12. And you're going to put x here, and guess what? The exponent gets isolated. It goes to the other side. The exponent just kind of jumps down. It's kind of like there's a little bit of a switch. Kind of like 12 gets shifted down, the x jumps to the left side, and a 2 jumps down to the right side. So part B is going to work the same way. What's your base here? E. So it becomes subscript. And you want to isolate the exponent, so I put a 9 here, equals y. And now what Maddie was saying, she mentioned ln. ln is what we call the natural log. I'll talk about that probably tomorrow. Or some people write ln. It's when you have base e. Log of a base of e is ln. There's a reason why we like using ln. I'll make that more clear tomorrow. But for now, I just care about you guys shifting things around. So now let's go the other direction. Well, if I give you a log, and I want the exponential equation. So now you got the log equation. Let's write it as an exponential. So really all you're doing is you're taking the 7 here and raising it to 3. Or you take the 4 here and you raise it to the y. So now your output becomes the input. The output being 3 for part A now becomes the exponent when you rewrite. So that looks like this x equals what to what power? 7 to the third, perfect. Or 26 equals what to what power? 4 to the y. Personally, for part B, I would just leave it like that. I wouldn't really necessarily do that, but because in order to do log in the calculator, I'll tell you how you can locate it. If you hit alpha, window, option 5. I'll show it to you guys right now. It's there too. It's in 2 places. Math, I think, option 9. I can't remember math. Oops. Yeah, it's option A. Or hit alpha window. It's right there also. So like log base 426, apparently is that. So 4 raised to the 2.35 power will be 26. So personally, for part B, I don't know if I would really do that. That doesn't really help us. It's just good to know you can do that, but it will be a lot easier to use a calculator to evaluate it. So, but for part A, that would help to be able to know how to switch that. And by the way, I've seen problems like part A on the ACT. For those who are taking next month or in April, they do those kind of questions. So it's good to make sure you have a solid grounding in this. The last bit will be example 5, and then we're done. And this I want you to do without a calculator. So one thing I'm going to do is I'm going to set each of these equal to y, just like we did in the formula that we have for logs. And we're just going to rewrite them and figure out y equals. So how would you rewrite log base 39 equals y? That would be rewritten as what to what? Good, 9 equals 3 to the y. Or for part B, 1 equals what to what? X to the y. So like looking at part A, what would y equal then? 2. Because really what you're saying is, hey, 3 to the 2 power equals 9. So basically what this is asking you to do, find the exponent. If 3 is your base and you want 3 to some power to equal 9, what's the exponent? 2. If 6 is your base and you want 6 to some power to equal 1, what's your base? Sorry, what's your exponent? 0. Or in this case, 1/16. So see, it's just reversed. They're just asking you to find the exponent. That's what these problems are doing. Before you were given the exponent, and it's easy. You just like 2 to the 4th power. Oh, 2 times 2 times 2 times 2, 16, right? Now we're telling you to find the exponent. Remember, logs help to isolate the exponent. So 1/16 equals 2 to the y. So what does y equal? Awesome, negative 4. Because 2 to the 4 is 16, but you got to make it negative to do the fraction. Then the last bit, we're almost done here, sorry, equals 5 to the y. That's 25 to the 1/3 power. Does anyone know what 25 is if you make it 5 to the power? 5 to the 2, right? Hopefully remember cube root is raised to the 1/3. 25 is 5 squared. So what does y get equal here? 2/3. Okay. Okay, so we're all set. It's good timing because that's kind of where I ended the other classes. So, all right.